The title of the presentation will be Multi-Timescale Control for Next-G Cellular Networks. So we're just going to give some brief motivation and why we want multi-timescale control in Next-G networks, and give an example use case of having an application of multi-timescale control in Next-G networks. So first of all, we have to first answer the question, what should next generation network support? So we all know that next generation networks, there are a lot of applications that are actually upcoming in terms of AR, VR, and all this IoT and all this kind of a lot of applications that are requiring different battery life and all this support for these networks. So, but despite this support for these networks, there are a lot of potential issues that these networks need to meet in terms of the spectrum is limited, and then networks are usually not focused on applications, are not application-centric, more or less, that they are usually human-centric kind of communication. And usually these devices that are using these networks are kind of battery constrained and energy constrained. So a way of achieving this next generation applications is through this RAN intelligence and automation. And one way is through this ORAN system, whereby we have AI and ML trying to deliver different needs of the RAN. And one important way is through this decoupled framework or hierarchical RIC architecture approach, whereby we have different AI and ML algorithms deployed at different timescales. So the idea of ORAN vision, which we all know, is to have this hierarchical RIC approach, whereby you have different non-real-time RIC, near real-time RIC, and then the new one that's coming up now, the real-time RIC. An example is the edge RIC that this research is ongoing on. And based on this different RIC architectures, there are different applications that could run on these different timescales, ranging from, in the non-real-time RIC, for instance, we have things like policy management and orchestration management. Then if you go down to the near real-time RIC, it's more or less like you have more applications like traffic steering, handover, spectrum sensing. And down to the real-time RIC, you have things like scheduling, MCS control, beam and interference management. So regardless of this vision we have, the idea is we want to leverage multi-timescale control to actually achieve all these kind of things. But current network have these limitations of not being able to meet these different applications due to insufficient granularity, and they are not able to meet different radio conditions. So the idea is that we want to bring this. Yeah, I don't know why these slides are on you. Sorry. Okay. So basically, we want some enhanced benefits with this multi-timescale control. Based on optimized resource utilization and increased flexibility and enhanced latency management. But we have some immediate use cases that this multi-timescale control can actually be implemented. And for instance, we have this multi-site spectrum management. This is an example use case. Then the other use cases, range from dynamic spectrum sharing and different URLC applications like V2V and V2X. So this talk will basically go into this application that we use to motivate this use case of multi-sites, to motivate this use case of multi-timescale control. So this is the multi-site spectrum management. So the idea is that we know that spectrum is scarce, and we want to maximize spectral efficiency under interference conditions, and also be able to densify transmitters so that we can improve energy efficiency. So the way we propose to achieve this is to have this distributed site management at leveraging this multi-timescale control at different RIC levels, so at the near real-time RIC and the real-time RIC. And then we have this real-time resource distribution to intelligently allocate available spectrum across different RAN sites. So this is like a basic system overview of our system. This is the Spark system, and so like I said, we are trying to achieve this multi-timescale control, and then we have interference classification being done at the near real-time rig, where we get these IQ samples and perform inferences, and then based on the decisions there, we send it to EDRIC that performs real-time distribution of resources among spectrum. So like I said, the key idea is to perform multi-time scale RAN monitoring and control. So the near real-time rig is performing spectrum sensing. So we deploy an XApp to detect external interference in spectrogram images. Then the real-time operation is going to be deployment of MUAP, that's at the EDRIC, to blank out resources and to distribute them to utilize the spectrum efficiently. So the way it operates is, okay, we have this big chunk of available spectrum, and then you notice interference at two different sites. So we redistribute this resource across the two sites by RB blanking and based on interference. So first of all, we talk about the AI-based spectrum monitoring. So we used this, so the idea is to get IQ samples from the RAN, and then through the E2, and then generate these spectrograms and perform some, use a pre-trained YOLO V8 model to actually do some bounding box decisions to be able to detect where the interference is, and then translate this to affected PRBs based on the numerology that we are using. And then this is just some training curves from the model. So we use the 3,000 samples, then we use this pre-trained YOLO V8 model containing this number of parameters. And so down to the resource distribution now across sites. So it's more or less like after the near real-time rig has successfully detected the PRBs that are being affected by interference, and so we then send that information to the EDRIC, to the database, to be able to make real-time decisions based on this algorithm to be able to distribute the RBs accordingly across different sites. So this happens actually every TTI. So it's based, so it doesn't interfere with any operation in the RAN. So based on the system implementation, this was the overall, we leverage srsRAN to implement this. So we had, we just did this system overview, and we did it over-the-air implementation in the lab, different sites, and connected to a near real-time rig to actually get the IQ samples and see the performance. So we also monitored the timing and the granularity of processing and control of the whole process from the near real-time monitoring, which we achieved to be less than a second, and then the real-time control, which is being done by the EDRIC, was less than a millisecond. And then we did different traffic profiles to actually understand how our system was performing in terms of in comparison with the base system. And we can see that we actually achieved better system throughput, and we also achieved better system SNR, and basically we also achieved less packet drops in system. So basically this is all. Thank you.